Hello students, welcome back, and let's go to the next topic, Cauchy-Euler equation. And I tried to put in all kind of different topics of chapter 5 into this single problem, and I think I succeeded. I was able to cover a lot of the different things. Here's the equation, Cauchy-Euler equation. As you can see, t squared times second derivative, t to the first power times first derivative, and t to the 0 power times 0 derivative. And then these are initial conditions. In this case, what do you do? Well, we have two different methods. One is changing these into appropriate exponential and then change it into a linear equation with constant coefficient. That's one way to do that. But the method I prefer is plugging in y equals to t to the mth power. Can we do that? Yes, we can. The reason we can do this is because of the fundamental theorem. We have unique solution, which means no matter which method we use, if we find out a solution, and that is the solution. So whatever method, whatever initial guessing, whatever educated guessing we do, if it works, then it works. There's probably a different way, but it doesn't matter. And that's what we are going to do. We are doing some educated guess, plugging in y equals to t to the mth power, and this is a derivative, and that's a second derivative. We have used this kind of idea before. A little bit more expanded idea was putting power series into this, power series and then derivative and then derivative. And again, the underlying idea was the fundamental theorem. No matter what kind of educated guessing you use, if you get a result, and that is the result, it's a little bit easier this time. We don't have to deal with power series, just t to the mth power is just fine. And then plug it into the original equation. I use a bit of color coding to help you see these things better. Put those into a second derivative, first derivative, and the original function, and then here we go. Now do you see t to the second power times m minus second power, multiply, and then you get t to the mth power, and also t and then m minus first power becoming t to the mth power. So if I factor t to the mth power out, this is what we get. And then when t to the mth power is constantly 0, which means y is constantly equal to 0, and yeah, it works out. And then if we have to answer the general solution of homogeneous equation, then you have to consider that trivial case as well, because, well, after all, if y is constantly equal to 0, we have everything equals to 0, so 0 plus 0 plus 0 is equal to 0. Trivially, it's true. Of course, that's not going to be the case in this case. Nonetheless, we'll have to do that if that were the general solution problem. But this is initial value problem, so you don't really have to consider it. You have to consider this part equal to 0, and this part with a name. I usually call it characteristic equation. Our textbook author calls it some different name. Was it auxiliary equation? I don't remember. And then the solution of this characteristic equations are typically called characteristic values or eigenvalues, German. And are they related to those eigenvalues in linear algebra? Indeed, yes. Anyway, let's go. Let's solve this equation. It's quadratic equation. It's not too difficult. And here we go. We have two solutions. M equals to 2i or negative 2i. So what does that mean? T to the nth power, where m value is 2i or negative 2i. So we get these two solutions basically. Y is equal to t to the 2i power. Y is equal to t to the negative 2i power. Maybe I should name them as y1 and y2 as these two. And then we can express the general solution as c1 t to the 2i power plus c2 t to the negative 2i power. Yes, we can write like this, and then you can even stop here if this were a general solution problem. But in this particular case, stopping here is going to be a bad idea because with these complex numbers, somehow you have to work out these initial conditions, and then you're going to end up with a bunch of equations related to complex numbers flying around. It's not impossible, and unique solution exists as the fundamental theorem says, but it's going to be difficult to deal with. So how do we handle that? That's the topic for the second step. Before going over the second step, let's recap. Euler equation, plug in t to the mth power, and the derivative, second derivative, plug into original equation, and then do some simplification. We have t to the mth power, t to the mth power, t to the mth power, factor all those out, and then we have an equation of m. Solve that, and then we're going to get appropriate solutions. If you have two real roots, that's going to be great. We have t to the certain power, t to the another power, and then you're going to get linear combination easily. If you have a double root, in that case, I hope you guys remember, you have to multiply log of t there. But what if you have complex number? Well, that's the case we are doing. Okay, all right. Let's move on. Turns out like this. T to the 2i power, you can use this formula here. A to the b power is equivalent to e to the b times, log of a power. And this is a useful formula that we had been using from college algebra days. But as a matter of fact, this is the very definition of general exponential. The usual exponential function we define like this. E to the z power is, let's see, anybody remembers this? Case running from 0 to infinity, and then this is z to the nth power over k factorial, and you can define your exponential function like this. By the way, this definition is valid in complex number system as well. And I hope you guys remember that Taylor series expansion and all. We can define exponential function easily. And if you establish that series, this infinite series converges using the interval of convergence, radius of convergence, and those kind of things, yes, this function is well defined. For arbitrary case, we define like this. And that we just did here. T to the 2i power, change it into natural exponential, e to the 2i times log of t. And now if you have exponential of pure imaginary number, then it is equivalent to cosine sine, or maybe, let's see, a, okay, plus b I power is the same as e to the a power times e to the b I power, and this is the same as e to the a power times cosine of b plus sine of b. I'm forgetting complex number I there. And this is the kind of formula you're using here, but there's a bit of a problem. With C1 and C2, how do they help? I mean, how do I drop these C1 and C2 and bringing back A and B? There are some questions to be answered. Now, you have to remember, everybody have to remember, if you have this exponential, then you're going to get sine and cosine. That's something everybody should be able to do. But if you're asked to prove, or if you're asked to describe what's going on in between, then you should be able to do that too. So here we go. In case you do not understand the last step, here it is. And this kind of thing may very well be a separate exam problem, not directly related, or perhaps within that problem as a separate part. There can be many ways. Let's consider. With selecting a specific values for C1 and C2, and strategic numbers are 1/2 and 1/2 respectively. As a matter of fact, I originally did just C1 is equal to 1, C2 is also equal to 1, and turned out some constant times cosine, and then the constant turned out to be 2, so okay, I start from 1/2, then eventually we'll just get 1, and you can do it. But in any case, if we start from 1/2, we get this beautiful expression here. y1 is 1/2 times exponential of 2i log of t. Excuse me, I should have increased the font. Yeah, too many exponentials. Oh no, I should not have. Okay. Okay, all right. So C1 and C2 are like this. And then apply those Euler expression of the exponential, cosine of theta plus I sine of theta. And then this one is negative, so cosine of theta minus I sine of theta. And if you add them up, oops, typo here, this should be 1/2. Yeah, this should be 1/2, okay. So this I part and this minus I part cancel each other out. You get only cosine part. So okay, by selecting C1 and C2 appropriately, we got one solution. y1 is equal to cosine of 2 log of t. Alright, let's find out the second solution, and that we can get by plugging in C1 and C2 as 1/2i and -1/2i respectively. How do I do that? If I plug those in, 1/2i, -1/2i, then we have cosine and the sine, cosine I sine, but then again this is minus, so the cosine part will cancel each other out. And this I and then minus I, another minus, so we're going to get 2i. So in order to negate that, I want 2i down there. Eventually that will give me 2 sine of 2 log of t. So we got two solutions. y1, y2, and how did you get those? By plugging in C1, C2 appropriate values. 1/2, 1/2, or 1/2i, -1/2i. Just strategically select those values, and then we get cosine and sine form. Okay, we got those solutions. Let's do a bit of a justification, because ay1 plus by2 form is a general solution, yes, but then again, that's when y1 and y2 are linearly dependent solutions. And we gotta check, right? Let's check. This step involves some unpleasant computations because you have to calculate the second derivatives and plug those in, but elementary. Okay, here we go. y1 is 2 cosine of log, excuse me, y1 is log of cosine of 2 log of t, excuse me, and y2 is sine of 2 log of t. And here, let's consider this one only. Never mind. Let's highlight everything here. Oh, wait a minute. Why am I losing color? Okay, all right. Okay, all right. y1 is cosine of 2 log of t, and then we have to plug those into this original equation. So we need to take the derivative and the second derivative, and here they are. Derivative computation, not too bad. Just apply the chain rule. Cosine becomes negative sine, and then multiply the derivative of the inside. And then the second derivative, we have to use product rule and chain rule. So we get this kind of derivative computation. A bit tedious, but elementary. After some simplification, this is what we get. And that's what I'm going to plug in right here, y prime and y double prime respectively. And here we go. Let's see. Yeah, that's original equation. and that's the left-hand side here. Y double prime red, Y prime blue, and Y green. And then this red, blue, and green terms go in accordingly. And let's do some computation here. T squared, that T squared cancel each other out. This T and that T cancel each other out, and then we got the second line. Now, break up these parentheses of this red term, we get the next. And do you see a cancellation? 2 sine of 2 log of t, 2 sine of 2 log of t cancel each other out. 4 cosine of 2 log of t, 4 cosine of 2 log of t, these two cancel out and we do have 0. And that's precisely what we wanted all along, which means this one over here, as we checked out, is a solution. As for the other function, it's a bit tedious, similarly tedious, and I'll leave the computation to you. Next step, are these two functions linearly independent to each other? Let's check, and let's check the collinearity. Is one function constant times another? Well, if you take the ratio of the two, do I get constant? No, I don't get constant function. We get tangent of something. This is not a constant. So these two functions are not collinear, not constant times the other, which means they are not linearly dependent. So they are linearly independent. That's one way to handle it. Another way to handle it is our textbook authors method, or as a matter of fact, every single textbook I checked so far. Every textbook I get uses this one as a default method. Not me. I'd much prefer to do it this way. And in order to justify that, we proved that collinearity thing in the previous section. Do you remember this problem? Yeah, we proved that. And then using that, now this is sufficient. Now, if you didn't prove it, or if you still want to follow the textbook authors method, then you can do this. Determinant of Wronskian, y1, y2, y1 prime, y2 prime, and then calculate the determinant. Cross multiply the principal, and then cross multiply the other, minus, and then we get this computation. And further simplification, cosine, cosine, we have cosine squared, sine, sine, we have sine squared, minus, minus cancel out, we have plus. So what do you get? We have cosine squared plus sine squared, that part is equal to 1. So what do you get? The total is 2 times t to the negative first power, or 2 over t, and that never hits 0. So this determinant, or Wronskian determinant, never hits 0. Consequently, this y1 and y2 are linearly independent. This is preferred method by the textbook author. Okay, now we proved y1 and y2 are, we found out y1 and y2, cosine of 2 log of t, sine of 2 log of t, and then we proved those are solutions, and we proved those are linearly independent. Now finally, let's check the initial condition, and let's find out what are those a and b. Those are just elementary. Y, and calculate the derivative, and then just plug in the number. Plug in t equals to 1. Plug in t equals to 1, and you have simple computation because log of 1 is 0, and sine of 0 is 0, cosine of 0 is 1. Here, you're going to get a equals to negative 3. Here, we're going to get 2b equals to 4. So we get what we want. A is negative 3, b is equal to 2, and what do you get? Here's a final solution. Y is negative 3 cosine of 2 log of t plus 2 sine of 2 log of t. If you want some checking, you can check those through Mathematica like this. Yeah, here's. And then left-hand side, you can simplify as 0. And the y of 1, y prime of 1, they are negative 3 and 4 respectively. Everything checks out.